to this computer. So we're starting again because I forgot to record. Welcome everyone to the ACM of this APL event. Checking codes in the corner. Welcome. Yeah, we had to do a lot of stuff to get the checking code to work, but now it works and we can use emojis for events later on. So today's agenda, we're gonna go over 4 topics. What is APL? The weird stuff, which is just the minutia, what's interesting about it. We're gonna go over some examples, and then we're gonna go into real world usages. Okay, so what is APL? APL is a programming language. Really, it doesn't mean anything. It's kind of like what SAT is now. It doesn't stand for anything, but it was based off of a book called A Programming Language, made in the 60s. Wonderful time. The central data type is a multi-dimensional array. So like it was made for like databases. It was made for like quick computation, mathematical computations. This is like potentially the oldest language I've worked with ever, but it's real interesting. Another thing to note is that this language uses a lot of special characters. You look at a traditional keyboard, most of the keys are not on there. So let's look at APL. So why should we use APL? First of all, it's a hipster thing. No one uses it, so we get to say it's cool. The other thing is parallel computing. It's very good at like matrix operations, and it is a functional programming language. So all the perks of functional programming languages come in there. Come with it, I mean. Cons, no one uses APL. So that upside is also a downside. Nobody, yeah, like it's kind of a meme. You can see videos from like the 70s, like BBC, black and white video showing like this guy doing APL on a typewriter. You're like, oh my goodness. It's an interpreted language. So that means it's like, Python's an interpreted language, but this one is also, so it can be slow. It doesn't compile well. Although due to the fact that it is based on the central data type is a multi-dimensional array, you can do matrix operations fairly quickly, or not fairly quickly. It's all relative, but it's not the slowest thing in the world. And also the keys. If we go into what APL uses, it uses all these funky characters. Some of these have made their way onto what we would think of as a traditional key set. You can see the plus and the minus and the asterisk and some of the slashes, / backslash. Then a lot of these ones are not on your keyboard.
One thing I would like to just add in real quick. If I obviously, because no one can type these symbols, we're not expecting you to mess around with anything today. But if you actually do want to follow along with the workshop, you can go to tryapl.org with the link I just posted in chat. And yeah, you can, there's like a bar at the top that will allow you to click on, and that will like let you type in these symbols into a command prompt type thing. And if you want, you can mess around with it as well. So yeah, this is not for the faint of heart, but if you would like to try it, then go for it.
Yeah. Okay, we're gonna go into some of the code. First of all, I think every good programming language needs comments. It's like, hey, doesn't that comment look like something?
Yeah, in case you didn't think this language is already pretty sus.
It's great.
Yeah.
We're cringe. We're cringe humans. I'm so sorry. Anyways, we can go into traditional arithmetic. Things to note. Here we put pluses and minuses and stuff like that, whatever, like the usual. But we also want to note that, say, there are a lot of weird things with how APL handles characters that we take for granted. So like in most programming languages, when you use an asterisk, you expect multiplication, but here there's an actual multiplication symbol. And same with division, the / is not a dividing symbol. You have to use the actual division symbol. Similarly, negatives use a high negative instead of just the regular minus sign. And if you use the minus sign, it alters the entire whatever is after this. We'll get into this, but remember that the language was made in the 60s and keyboards look like this. It wasn't really anything like a standard. So when you decided to code an APL, you got a keyboard that supported APL. The next thing we can go over are arrays.
Oh,
We
what the hell?
said that.
I swear I fixed the formatting for this. Oh well.
Ah, dang. Oh, it's okay.
Oh no. That's
So
awkward.
we again went into it is yes, it is very strange. So all data in APL is stored in arrays. We said it was the core structure of the language. It's an array is just a collection of numbers, characters and arrays. We can like interchange them. Characters can be stored in quotes, or we can create an array of characters, which is a string. It's wonderful. APL has lists technically, not really. They use arrays. No, I'm gonna ignore you from now on. I'm not looking at Lisp anymore.
Yeah.
One
So
D arrays.
so essentially the deal with APL is that you have so arrays are basically you type with like items with spaces in between them, and then you can use functions to do stuff with them or combine them or whatever.
Mhm.
So yeah.
Yeah, and then if you want to list in a list, you use parentheses, and then like an array and an array, you use a parentheses. You can go. We can use the equivalent sign to check the depth of an array, how much nesting there is. Very simple. If there are, I can't remember what uh, an array that contains both vectors and scalars gives you a negative sign or a high negative. I'm sorry, let me phrase that. High negative, proper terminology. And yeah, it's just there are weird nuances with this language too. If we go into like array manipulation, if you think of like Python, where you're trying to change the size of a 2D array or reshape it, you have to use like NumPy or whatever. In APL, it's really built in, so instead of using another function, you can use something like row, which is R for reshape, but looks like that. It looks like a P. Uh, very strange, but very useful at the same time. Um, there's also topics like, actually, wait, do you have anything to say, Kyle? Sorry.
Not really. It's
Mhm.
basically okay. Yeah. So this operator basically just takes the array on the right, looks at the array on the left, and reshapes the array on the right so that it has the shape that's on the left. So 1, 2, 3, 4 is a 1D array. We reshape it to be 2 by 2. So yeah.
Mhm. Then you can say you can do like 3D or multiple dimension arrays. We have a 232, which creates like a cube, 2 by 3 by 2 cube, and then it just displays each like layer in the new line. It's great. Don't worry. More manipulation. We can see that like if you reshape to a size that is too small, it'll cut off the tail. If you reshape that's too big, it'll start looping. Um, it'll go over until the entire space is filled. And I'm going to pass it on to Kyle for the functions.
All right. So we've talked about a bunch of operator symbols before, and those are actually functions. So how functions work in APL is that there are two types of functions. There are functions that take one argument and functions that take two arguments. So most of the operations we've covered are operations that take two arguments. So we've covered like addition, subtraction, the reshape, and yeah, and those take an argument both on the left side and right side, and it'll do stuff to combine the two. Those are called dyadic functions. Now now there are also functions that are monadic, and if you've been to my Haskell workshop, they're not related to monads at all. Just so don't worry about that. All monadic function, all the word monadic means in this context is that it's a function that takes one argument. So we have the examples I've listed here are negation, row with one argument, like returns the shape of the right argument, and we have depth as well, which returns the depth of the array given to on the right. And yeah, in case you haven't noticed, depending on how you use different symbols in APL, they can either be dyadic or applied dyadically or monadically. So here we have 10 minus 7 applying the subtraction operator in the dyadic applying the minus symbol in a dyadic way. So you get 10 minus 7 minus 3. And here we have minus 5, which gets applied monadically because it only has one argument. So we have a high negative 5. Next slide. All right, so here we get to the reason why we always say to use a high negative when you want to negate a bunch of numbers, right? So here we have a negative symbol followed by 2, 1, 4, high negative 11, 6. So what's happening here is that the negative here is, so what happens here is that this function gets distributed through all of the elements inside of the array. So if you do a negative right before, if you do like a normal negative symbol right before an array, it'll actually apply the minus to all of the elements in the array. And notice how that doesn't actually, notice how the negative 11 only, well, notice how the high negative 11 acts like a normal high negative 11, like normal negative 11, like you'd expect. Here we have a more complicated example down below where we where the negative gets applied to, oh wait, what the hell? Oh, so what happens in the more complicated example is that the negative gets distributed through every single element in this multi-dimensional array. So yeah, just something to know. Anything to add, Chris, or are we good to move on?
Good to move on. Next slide.
Sick.
All right. Oh yeah.
Yeah, so here are basically all of the dyadic, monadic arithmetic functions. So the negative symbol is negation, or in a dyadic context is subtraction. The division symbol, when applied to only one operator, is, well, one operand is reciprocal. So it actually takes the argument on the right and then it takes reciprocal. So it does the 1 over the number, or 1 over all the elements in the array. Plus is actually complex conjugate. So so in APL there's also complex numbers, and you can do operations on them like so. It takes the conjugate of whatever complex number or array of complex numbers. Times returns the unit complex number in the direction of its argument. So it just takes the well, it takes a complex number and it normalizes its length so that it's of length 1, or it just does nothing if it's a real number, I believe. But yeah, and asterisk actually raises e to the power of its argument. So instead of multiplication like you'd normally expect, it actually raises it actually takes e to the power of whatever's on the right. And if you have 2 operands that you use with it, it will just it will take the left side as the base and the right side as the power, I believe. So yeah. All right, here are just some examples of how these operators are applied. So here we have, so let's break down this first example. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 that is reshaped into a 3 by 3, and then we divide each element by 9. So here the divide by 9 gets distributed into every single element of the array on the left. So we here we have 1 divided by 9, 2 divided by 9, 3 divided by 9, and so on. So we get a grid, a 3 by 3 grid of numbers divided by 9. So yeah. And in the second example, we just have on the left of the way to read this is that the element on the left of everything to the left of the asterisk is one single array that's just multi-dimensional. And then each of those gets raised to the power of 2. So here we have 1 squared is 1, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, and 7 squared is 49. So yeah, scalar function operators get distributed throughout all the elements of the array. We can also take element-wise operations between 2 arrays. So what's actually happening here is that 4, 3, 2 is one array and 3, 6, 4 is one array, and we subtract the 2 arrays, which means that we take the element-wise subtraction of each. So the result is the element-wise subtraction between the 2. So 4 minus 3 is 1, 3 minus 6 is -3, and 2 minus 4 is -2. What's happening here down below that is that we can also assign variables in APL. This is probably pretty intuitive. So length gets assigned 20.5, height gets assigned 13.1, area gets assigned length times height, and then area is 20.5 times 13.1. So there you go. Lastly, we have the here we divide an array by another array, and what happens here is that 423 gets because the array on the right is an array of arrays. Each element on the left will get divided by the corresponding element on the right. So 4 gets divided by 1, 1, and 5 because the first element of the array on the right is 1, 1, 5. So here we get 4, 4, and 4 divided by 5, which is 0.8. Likewise, for the rest of the other two sections of this output, we have 2 divided by 1, which is 2, 2 divided by 5, which is 0.4, and 2 divided by 1, which is 2 again. And lastly, we have 3 divided by 5, 0.6, 3 divided by 1, and 3 divided by 1. So yeah, there you go. Very cool. Here are just some more examples of the arithmetic of arithmetic that we so yeah, the times symbol works as you'd kind of expect. So you can multiply numbers to get, you can multiply numbers together. And
why can't they just use normal symbols? This is because this was in the 60s. Keyboards weren't like standardized. So like, who is to say that in another alternate dimension, instead of when we press Shift 8 on our keyboard, instead of getting an asterisk, why wouldn't we get the circle with a star in it?
How
See, but they weren't
suggest that?
standardized. They
Yeah.
weren't standardized.
I don't think when was C written?
When
I
was
don't
C
remember.
written?
When
Good
was C
question.
written? The 70s.
70. So
Yeah,
this is
so-
older than
so-
C.
So this predates C, which is incredible to think about. Like, holy crap.
Wait, didn't
Okay.
Pascal predate this and that have quote unquote more standardized symbol?
Um, Let's see. Pascal was I can't find it. Where's the date? 1970. First appeared 1970. This was made in the 60s. I'm
What
sorry.
the hell?
Okay. mute
Why am I
yourself.
learning a language or
It's
because
okay.
we like to learn weird stuff here at ACM. So
This
anyway.
is not meant to be useful. This is more meant to be an educational tool. One of the stepping stones of programming languages.
Indeed. But yeah, here we just have some more examples. Here we have an example exponentiation. Here we have a circle with a star, which is logarithm. So I believe this is 64 log. No, wait. This is log 64 base 2, which is 6, because 2 to the power of 6 is 64. Okay. And here we have, when you apply the star with circle monadically with one argument, you get the natural log. So natural log of 1 is 0, and natural log of the e to the power of 23.14 is 23.14.
The next one, okay, so floors and ceilings, they work traditionally as expected. We use a symbol for it, floor and ceiling. It's great. These L's, they can act monadically and dyadically again. So if they act dyadically, then for the ceiling, it'll essentially put us like, put a floor for whatever list or array you use on the left, and then the right is the boundary. So anything less than the boundary is set to the boundary. Anything greater than the boundary is set to it's kept. Opposite for the other one. And then at the end we have the bar symbol, traditionally, or what we would call the bar symbol. That is actually a magnitude or the absolute value. When it's used monadically, it is the absolute value. And then when it's used dyadically, it is the modulo. Not sure where they got that one. I would have thought some altered version of the division symbol, but it's okay.
Oh, just a quick note. This is actually backwards from how we usually apply modulus. So it's what actually happens with the mod in APL is that you take the stuff on the right and you mod it by what's on the left. So we have to think reverse from how we normally think. So here we have here in the output, let's take like let's say look at the number 4. So 4 mod 3 is 1. So, and 3 mod 4 is 3. So here we can see that the element and in element where 4 is 1, which means that we've taken 4 mod 3. So yeah.
Then we have dynamic functions as well. We can assign value. We can assign functions to like other values. The way it works is instead of just putting in a value, you use curly brackets, and we have to use the alpha and omega symbols. The alpha symbol signifies the left parameter. So when you use the function, you need to like 4 times 5. 4 would represent the alpha symbol, and 5 would represent the omega symbol. So we can have, for any dynamic function, we can have 2 parameters. We can stack them inside. So we can see as we continue down to the bottom, 3, or the very bottom example, you can like stack them together, use multiple times. Also, we can just use them, what is it called, as anonymous functions. So you don't need to actually define like times. You can just put it in there and it'll work out. Next, we have Boolean Singletons. So just Boolean expressions kind of thing. We can set it. The format is if A, then B, else C. So for the first example, we have W colon true, diamond false. So W is 1, which means it's true. Then we go to, oh yeah, I forgot to say, much like many other languages, any number that's not 0 is true, and any number, and then if a number is 0, it's false. So we can get true false statements. Similarly, we can use other Boolean expressions or operations to see like 6 is greater than 4, we get 1 because it's true. If we do it the other way, we get 0. We have the equal sign, which we use for equivalence or checking equivalence. So this is another case of comparing arrays. 2 arrays, if they do match, say index 2, 4, and 5. I forgot to say that arrays in APL function with an index of 1, which is kind of frustrating, but whatever. Much like MATLAB. Similarly, we can also use Boolean singletons inside of dynamic functions as our bottom to see that like to get an output. Recursion, our favorite thing in the world, as a functional programming language. We have where is it? So we can try to use recursion as we typically do, which is just recall itself inside of the function declaration, or we can just use the nabla, which is the upside down delta symbol, and that essentially puts the function it's inside of itself. Funny quirks, very interesting. Why isn't this in Haskell? Sorting is one of the really cool things about this language. So when we sort things, like we can go over this example. We create V and we input this array 3, 1, 4, 1, 5. If we use the tree symbol, it takes the array and returns the indices of the major cells in ascending order. So we can see that, oh, what's this number that it outputs? 2, 4, 1, 3, 5. Where'd they get that? And then we can see the second index is a 1, the fourth index is a 1, the first index is a 3, the third index is a 4, and the last index is a 5. Then we can do some very quick and aesthetically pleasing sorting. So if we take V and we rearrange it using the indexes or indices of the sorted V, which gives us the index or indices, then we get the sorted array. And it's very easy. The other thing we can note is that, say, if we have a reshaped matrix and say M, you can see a 2, 7, 1, 8, 2, 8. We can also sort that again, and then it'll give us the indices of its sorted nature. So we get second index, which is 1, 8, and then we can see that it does 1, then 3, because there's a 2, 7, and then a 2, 8, and then the 8 is larger, so it goes at the very end. And then to go backwards, we just use the upside down tree, down arrow tree symbol. Same exact thing, except it returns the indices in reverse order. Boolean functions, we did this before a little bit. forgot to put this in the right place. Similarly, you can use and or NAND XOR, or not XOR. There are more of these, but these are the 4 main ones that are given symbols. And then, if you have CSE 140, if you have any of these, you can create any other Boolean function. Let's see. So we have some examples here. We have the simple true false statements based off of it. We don't have to go too in depth with these. We're kind of running out of. Oh, are we on time? We are on time actually, but these are kind of annoying. What if we had and or etc. on our keyboard? Well, you can if you want to. Kyle has learned how to remap his keyboard, so when you press Alt and Shift, you can access these APL keys on a traditional keyboard. Why use 4 characters when you can just use 1? We can always minimalize even further. Why have any characters? Why have any words? Let's speak in beeps. Now I'm gonna hand this to Kyle.
I'm really excited about this part because what's cool about our checking code is that not only is it weird, not only does it look super weird, but it's also a function that calculates prime numbers, which is crazy. Okay, so yeah. Here we've defined a function called primes, which takes 1 argument on the right, and it basically does a whole bunch of random crap to it. Well, not really. I'm going to explain what it means. But essentially what happens is that primes 10 gives 2, 3, 5, 7, and primes 20 gives 2, 3, 5, 7, 11, 13, 17. Okay, so it basically generates all of the primes from 2 to the number you input, which is super, super cool. And we're gonna break this down. We're gonna explain how this works. So, yeah. Next slide. Okay. So I think Chris, you just gotta okay. So we're gonna break this down from right to left because the function gets applied. Functions get applied. The functions on the right get calculated first. So we're gonna go right to left, and then we'll gradually figure out what the hell this means. So. This funny eye looking symbol basically generates all of the numbers from 1 to the number that you give it. So funny eye of 10 will give you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's what that does. And then we come to this funny looking thing. So here we have 4 symbols. What do they mean? Well, let's start with this funny tilde thing with 2 dots above it, the really confused looking face. So what this basically does is it say, hey, let's take the argument that's on the right of this thing and apply it as both the left and right operators on the left for the function on the left. So as you can see, I've broken it down in the comments here. So funny eye looking symbol 10 gets applied on both sides of this operation. So now coming to the dot, the circle and the dot. So that basically takes a function on the right, and then the output is a function such that it applies that function element wise for elements on the left and right. What the hell does that mean? So as I've explained below, so circle dot bar applies the modulus symbol for 2 arrays element wise, which means that it will take 1 element from an array on the left and 1 element from the array on the right, and it will combine them. And it will do this for every possible combination of elements on the left and right. So this, if you do one more, Chris. So what this line, what the thing on the bottom does is that it takes 1, 2, 3 and 1, 2, 3, and it will take all combinations of those 2 arrays and do like an element wise like modulus of the 2 arrays. So here on the top right is 1 mod 1. The top left is 1 mod 1. Top middle is I believe all 1 mod 2. No, it's 2 mod 1. So I'm getting confused. So yeah, so row I and column J denotes J mod I. So that's 1 mod 1. This is actually 2 mod 1. And then top right is 3 mod 1. But let's do like bottom left is 2 mod It's one mod 2. Yeah, it's one. No, it's 3 mod. I'm sorry, I'm getting really confused. So it's 1 mod 3, and then bottom middle is 2 mod 3, and then bottom right is 3 mod 3. So you kind of get the picture. It basically just performs an element wise mod. So next slide. Now that we have that, we can use that square matrix to kind of generate so now what we're going to do is we're going to pick out all of the elements that are 0, because what the zeros mean is that if you think about like a grid of numbers, and you basically what we're basically doing is we're picking out the elements that are multiples of the row index. So yeah, so each column is going to contain, each column of this resulting matrix is going to contain ones at the indices that are equal to a factor of the column index. So in the first column, what we're going to get is we're going to get 1 at the very top left corner and 1's nowhere else, which means that only 1 is a factor of 1. In the second column, what we're going to get is, I should have really drawn this out, but in the second column, we're going to get 1 at the top and then 1 at the second row. So 1, 2, and then that basically means that 1 and 2 are factors of 2. In 3, we're going to get 1 at 1 and 1 at the top row, and then 1 at the third row. And in 4, we're going to get 1 at 1, the first row, the second row, and the fourth row. So what we can do, what that gives us is basically where a list of, think of it as like a list of columns where you have a 1 where the factors are. And then once we sum up all these rows using these two symbols here, so what this does is that it takes the function on the left, it applies it to all of the, it takes the function on the left and it basically just reduces the array on the right using that function. So it combines them all using that operator. So this combines all the rows. So this will give you a list of numbers from 1 to whatever. Here in this case, we have a list of numbers from 1 to 10, where it basically counts the number of factors that there are for each number. So it should give you 1, 2, 2, 3, 2. Yeah. And then because we want prime numbers, what we could do is we can pick out the numbers that are equal to 2, because prime numbers are defined as numbers that only have 2 factors. So when we do 2 equals the mess that we just created, now we can pick out the indices where there are prime numbers, and then that I symbol with the underline basically gets us those indices. So we're done. That's our prime function. Very cool. Very awesome.
Yeah, we can highlight a little more of that. So like,
yeah, try APL might be a lot better to.
Yeah. So where's our check-in code? There it is. I just need to scroll up. So if we put this in here, we can get our. Not work. There we go. So we get our prime numbers. We can go back and see what I was talking about. So just the first part gives us. Oh, why is it inverted? Let's see. Oh, I need to do.
No, that's actually correct. That's actually correct.
So we're checking which ones are 0 and which ones are 1s. So we want to look for the ones that are just 1s, or 0s turn to 1s, and then anything else turns to 0. Okay. So this first heading is for the number 1. 1 is divisible by 1 and nothing else. So that's our first one. This is the heading for our number 2. 2 is divisible by 1. 2 is divisible by 2. That's 2. We do 3, divisible by 1 and divisible by 3. We go to 4. It's divisible by 1, 2, and 4. What we then need to do is we need to check which of these. Or wait, let's sum it first. So now we can sum all of our columns, and or headings. Sorry. We can see number 1 has 1 factor, or 2 has 2 prime factors, 4 has 3, 5 has 2, 6 has 4, and then we can figure out, as we did in this one, which ones have have 2s in the factor. Then we can do our, where's the where index symbol in order to get the indices of these. Remember that indices start at 1 in APL because there was no standard back then. Thank you, C. Thank you for doing that for us. Now our last section, we'll go over some more examples in a bit, but we're going back to real world usages. And I'm sorry to say, there aren't any. It is kind of sad, but it's very understandable because we look at languages like this is GitHub. I pulled up the GitHub repos to see how popular languages. You can see something like JavaScript has 6 million, Python has 3 million, even C has almost 1 million repos that use the language, and APL has around 2,000. It is not a popular language. There is one company. Oh wait, where is it? Oh yeah. It's wonderful because there's one company, when we put tryapl.com or org on the website, it's run by this company called Dialog, and they are the only company potentially in the world that still maintains APL as a language. For what reason? Who knows? Potentially, this might be a very flawed metric just looking at GitHub, because there are probably some companies that use it in the back end because of legacy issues and it's technically maintained. We can get a sense of like how little it's used. No one talks about it. I was going to pull up an example, like the last commit that had APL in it was like 6 months ago, unlike Python, which was like 3 seconds ago. And then we can just look at individual files. For Python, there are over 300 million files that have the py extension, whereas there are only around 3,000 that use the APL file header. So this is a dead language. It's like Latin. It's a dead language. No one uses it, and if they do, it's because they're intellectuals or they're memeing. And I think we're big memers. So thank you for surviving. We were supposed to give this code out at the end so that people could check. People who stayed at the end would have an easy time checking in. But I guess the checking code got circulated in the chat. But congratulations. I guess we're done now. I'm going to stop the recording. If any of you have any questions or concerns, we're okay. We're healthy-minded individuals. We were not forced to do this, except by our own volition. Thank you very much.